Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, count the number of substrings with dominant ones. And I'm not going to lie, I was really planning on watching the Lakers game today, but I guess I'll record this video for you guys because the problem description is really short, but unfortunately it's a really complicated ass problem. There's so many edge cases. Like I could explain the general intuition to you, and I think you'll understand it, even though it's not easy. But really getting around those edge cases is a pain in the ass. Like it took me forever to fix all the errors with my code at least, but it's kind of a clever solution to this problem. So I'm just gonna explain the solution to you guys. I'm not gonna really go super in depth into how to come up with it because honestly, we'll probably be here for hours. I think just explaining the solution and the intuition behind it will teach you a lot. So the idea here is that we're given this binary string with zeros and ones, and a substring is defined to be dominant, or it has dominant ones. Let's just call it valid. It's considered valid if the count of zeros, so let's just use zeros for that, squared is less than or equal to the count of ones. And so what we want to do is count all the substrings where that's the case. Now we know that we can definitely solve this problem in n squared. That's going to be the brute force solution. So we should try to come up with something better than that, given that this is a medium problem. And I would even argue that this is honestly a lot more difficult than a lot of the hard problems I've personally solved, but maybe you disagree. So we're going to try to do better. My intuition was trying to come up with some kind of sliding window or prefix sum approach, maybe get this down to linear time. Maybe that's possible. I don't actually know, but I definitely couldn't come up with it, and I didn't see another solution with that. Maybe I missed it, but the solution is actually going to be n times the square root of n. So that's why this is such a hard problem, because nobody really thinks to come up with a solution like this. But the intuition behind it is actually pretty clever, and I'll tell you why. So the general idea here is that in the worst possible case, given that the size of the input is n, we're trying to keep the count of zeros squared less than or equal to the count of ones. The max possible value for the one count could be n. So what's the max possible value 0 could be? Well, obviously, a 0 squared in the worst case could be proportional to n, but when you take the square root of that, you get 0 to be, like in the worst case, the biggest it could be is the square root of n, because if you square that, then you get back to n, so then the inequality holds. So that's like one main observation you have to make. Again, who even thinks to go down that line of thinking? But once you do, part of the problem kind of opens up. It doesn't become trivial, but it starts to open up. Because the idea intuitively isn't too different from the sliding window. So like think of it this way. Let's say we have 2 pointers, left pointer and right pointer. I want to count all the valid subarrays starting from here. We can't do the naive sliding window, and let me show you why. Because the naive sliding window, it relies on the fact that we can eventually, based on some condition, take our left pointer and start shifting it to the right. So like maybe this problem could have been different, and they say the max number of zeros we're allowed to have in our window is 3. Let's say they gave us something like k equals 3. That's the max number of zeros. What we would do is like keep extending our window until maybe we got to somewhere like this, and then we'd see, okay, our window is invalid now. So we have 4 zeros. We're only allowed to have 3. Then we would take our left pointer and shift it to the right. We can't do that super easily with this problem because like I get to this point maybe over here. I have 3 zeros so far, but who knows? Maybe I have a bunch more ones coming up. At no point can we easily say that our window has become invalid, except if you make that observation I made a couple of minutes ago, where we know that the max number of zeros can be the square root of n. So that's like a very, very key observation. So actually in this case, we would like get to here, maybe with our right pointer, we'd say, okay, the count of zeros is 3. And we know the square root of n in this case is 5. Clearly 0 has gone above that. So at that point, we can confidently say, okay, let's go ahead and shift the left pointer to the right. Okay, but in terms of actually then, like within the window itself, counting all the different substrings that satisfy the condition, it's still not going to be trivial. So actually, we can't just keep the right pointer there. So we can't use the typical sliding window approach. When we do decide to shift our left pointer, this is what we're going to do. We're going to shift it by 1, and then we're actually going to start our right pointer from there as well. So right is also going to start from there. Okay, so now you're probably thinking, well, this just looks like the brute force solution where we have like some kind of early termination for if like we have too many zeros. So even like in the worst case, this might still run in n squared time. And you're right, but that's where the second trick comes in. This right pointer, actually, we're not going to increment it 1 by 1. We're going to still use the fact that the max number of zeros we can have is square root of n. And so rather than incrementing the right pointer by 1 each time, we're going to do something very clever. We're only going to shift it to the next 0. So here's the next 0. I'm going to shift it. Now, maybe there's another 0 over here. Now I'm going to take this guy, and rather than shifting it here and here, I'm just going to shift it all the way to the 0. So this will guarantee that the max number of times that this right pointer is shifted is going to be square root of n, because at every step we're introducing a new 0. The max number of zeros we can have is this many. So that's the worst case. Okay, if you've followed up until this point, you probably think you're really close to the solution. That's what I thought too. But this is where the math and a lot of the complicated stuff comes in. So now I'm just going to go into actually explaining the algorithm. I'm not going to waste a bunch of time on the rest of the intuition. I will try to explain the math and stuff like that, but let's switch to a different example now. So this is the example, and the result of this example is 16. I'll just kind of quickly visualize it. So this is going to be one subarray starting from here. This is going to be a second one because this is, there's 1 0, there's 1 1. If you square both of them, they're equal. And then this is a third subarray where 2 is bigger than 1 squared. And then this is another subarray, 3 is bigger than 1 squared. And then here, this is actually not a valid subarray because 2 zeros, so 2 squared, is bigger than the 3 ones that we have. So we don't count that one, but I do think we can count this one where we have 4 ones and 2 zeros. 2 squared is 4. So that's good. And I'll just kind of quickly go through the rest of these. This is not valid, but this one is, this one is, this one is not, and this one is also not. And then from here, we have this subarray, 2, 3, and 4. But now starting from here, we have 1, 2, and 3. And then from here, that doesn't count. This one does. And lastly, this one does. So if you count all of these, I do think we're going to get 4 plus 2 plus 5. That's 11. And then I see 5 more here. So that is indeed 16. So if you want to know the solution to this, it is 16. I just showed it to you. And I highly recommend you kind of do some of this example stuff on pen and paper yourself. I promise you that's the best way to build intuition. Watching me do it is definitely helpful if you're like completely stuck. But if you think you have an idea of what you're doing, highly recommend trying things yourself. But okay, so we have that. And one thing we know is we're going to do those 0 hops. So we're going to do them from left to right. So what I'm going to do is build sort of an array up above. Let's call it next 0. So it's going to tell us for every single position, what is the closest 0 to the right of it, not including itself. So just to show you what that array would look like, it would be pretty simple, and I'll show you how to fill it in the code. I think it's just going to involve going through this in reverse order. So like, for example, initially for all of these, we'll set it to n, where n is the size of the array. So the size of the array is 6 right now. So that's how we would initialize everything because we assume that there aren't any zeros. So this would initially have a value of 6. And that makes sense because there's nothing to the right of it. So even if this was a 0, it would still be 6 because there's nothing to the right of it. But As we go to the left, over here, we're going to see, okay, is my next neighbor a 0? Because if it is, then I can put 5 over here. But if it's not, then I'm just going to put over here whatever was over here, because this tells us where the next 0 is for this guy. So right now, this is not a 0, so we put a 6 here. And then over here, we see, okay, next guy is a 0, so I'm going to put 4 there. And then for this, it's not a 0, so I'm just going to replace it with that. And just kind of keep going like that. So 4, now we get 1. And that's pretty much it. So from here, this tells me the next 0 is going to be at 1. From here, this tells me next 0 is at 4. And then same for all of these guys. And then over here and here, they're going to tell me to go out of bounds because there is no 0. So mathematically, it's consistent. So this is the easy part. Next is going to be the actual math part. So I'm going to have my 2 pointers. I'm going to have my left and my right pointer. You can say initially they're going to be over here. And I'm also going to keep track of the 0s and the 1s. The 0s are going to be really easy to keep track of because every time we shift our pointer, like I'm here, we do need to know what we initially started with. So initially we didn't start with any 0s and we have a single 1. But every time I shift, I'm going to be introducing another 0 to our set of 0s. But at the same time, I'm possibly adding multiple elements. Like here, I just added a single 0, but here I added another 0. But how is it clear that how many 1s we have? Like we can't just track those one by one. That would defeat the purpose of doing this multi-step hop. So the easiest way to do this, you probably guessed it, is just get the size of the window and then subtract the number of 0s from that, and that'll just give us the number of 1s. So again, just a little bit of math you need to keep track of, but it's going to get a little bit more confusing, so stay with me. Initially, like I said, we're going to keep track of these, and we're going to keep pushing the left pointer as much as we can. We're going to say that this window does have the possibility to create valid substrings for us as long as this condition holds. 0s squared is less than or equal to n. As soon as that's not the case, well, then we can just stop shifting the left pointer and we can start at the next position, counting subarrays from the next left position. But so far we haven't seen that. So here we have 0 1s from this left pointer. We're trying to right now do a single hop. We do see that next 0 at index 0 is going to take us to pointer 1, position 1. So that's where our right pointer is trying to go. But we're not going to quite put our pointer there just yet. Right now, I'm going to put, let's say, the next pointer there. That's the next 0. So what we want to do right now is count how many valid windows we had before we introduced this 0. And that makes sense because so far we just started, we just have one element. So of course we would want to do before we add any more 0s. Maybe this is already a 0, maybe it's not. So in this case, the base case, it's very, very simple. The first case, that is. We would see we have 0 0s. How many 1s do we have? We would take the size of the window. It's 1. We would subtract from that 0. So we have 1, 1. And then we would check, okay, is the number of 1s greater than or equal to the number of 0s squared? Yes, it is. And again, this case is so simple. It's just a window of size 1 that we would just take to the result and add 1 to it. So since this case is so simple, I'm not going to show you the general math formula because I think it would just confuse you for this case. But the math formula is the hardest part. Knowing how much to increment the result by, that's the hardest part. That's what I want to spend a few minutes on. So again, this case is very, very simple. But now let's consider the more general cases. So now, as we updated our result should now be set to 1. We're going to now actually shift our right pointer to that next position. So now right pointer is going to be actually over there. So now we're actually including the 0 in the window. Before we weren't. And since we are including the 0, we should definitely increment the number of 0s. So this is now going to be 1. And now, once again, we are going to, for this position, we're going to look in the next 0s array, which is 4. So we know that that's where the next 0 is. So I want to put the little next pointer over there for now. The reason we're doing this is because we want to know how far can we extend this pointer without including any 0s just yet. And remember, I'll just leave this marker here for this is all we've computed computed up until this point. We actually haven't even included this 0 in our window. So this result is just this part of our array, starting from here and ending here. But now we've gotten all this extra stuff before this 0. So how does this possibly contribute to the result? That's the hard part. Well, first, let's do the easy part, which is update the number of ones. So now that the pointer is over here, we can update the number of ones before this pointer by taking this pointer, subtracting the left pointer. And if this was actually inclusive, we would do the +1, but since this position actually is not inclusive, that's why we don't do the +1. So we can just do next minus the left pointer. That'll give us 4 minus 0, which will give us this distance. Or you could also think of it as this distance, but they're both the same, so it doesn't matter. But in any case, that'll give us the size of the window. It's 4 elements in the window, and we will subtract the number of zeros. So that'll give us 3. We have 3 ones in the window right now. So how do we update the result? Well, first things first, you have to recognize that we don't want to include any windows that ended before this point. So in the best case, the most windows that we could have added is going to be like the distance that we went. Because in the best case, every window ending at one of these new positions was a valid one. And in this case, that actually is true. So we would add 3 in this case. So that's like the best case, this distance. But there is another case, and it's kind of hard to illustrate that with this example. So let me just kind of change it and say that what if instead of this being a 1, it was actually a 0? Then it's kind of clear that we definitely can't say all 3 of these windows were valid. We can't say all 3 of these guys were valid. So we were trying to be greedy and just say, just give me all that distance and add it to the result. But we can't quite say that because look at this. We do see that this window is not valid. And we do see here, this window is also not valid. 2 squared is bigger than just 1. And actually, we also see that this window is not valid either. 2 squared is bigger than 2. Now, I'm not going to cover exactly what we do in that case. I think it'll probably make more sense because I think that case is coming up in the next iteration. So I'll save it for then. But for now, let's assume that we could have added the 3 to the result in this case. So I will just put that +3 over here. So now I'm just going to clean some of this pointer stuff up real quick. So we were at 1, 0, and our next pointer was over here. And now we're going to include that 0 in our zeros. So we're going to put 2 over here. And now our next 0 is going to be at pointer 6 because we're hopping from here to there. So I'll just put this line over there. And let's say our next pointer is here. It's technically out of bounds. And that's part of the reason why we weren't taking this. And as soon as we saw that 0, we weren't adding it to our count of zeros because we actually don't know if it's real or not. But we do know for sure that this is the boundary that we just gained this much distance. Okay, so now what we would want to do is, again, see how many of the subarrays here are actually valid. In the best case, we would get 1 and 2. But are both of these actually valid? It looks like, so this one has 2 squared versus 3, so that one's not valid. And also this outer one over here, we get 2 squared versus 4. So that one actually is valid. So only one of them is valid. This one is not valid, but this one is valid. So how would we handle this? Our result so far, I believe, was 1 plus 3. And so far, we've only considered the windows that are actually starting from here, where the left pointer is actually over there. Well, again, let's start with the easy part. We see here, this is at position 6 minus left. That's going to give us a size of 6. We subtract the 2 zeros. That gives us 4 ones. So we do have a count of 4 for the number of ones. So now, oh, and also our right pointer is still going to be over here. So if we were still trying the previous approach, we would just take the next pointer minus the right pointer. That would give us this distance of 2. That would say, okay, we introduced 2 new valid windows, which we can then add to this. But it's not 2. The actual answer to this is 1. But why is it 1? What's the formula that we can use for that? Well, that's where this math part is going to come in. And this is probably the most confusing part. Well, you might understand it, but coming up with it, I think, is not super easy. But the general idea is keeping track of the extra ones. How many extra ones do we have? Because one thing to note is that this is where we were previously, right? That's where the next pointer was. That's where the cutoff was. That's why I drew the line over here. And then we took this guy and we moved it all the way over here. Now, we know for sure that everything in between that was a section of contiguous ones. And so now the only question we have is how many extra ones did we have? Because that will tell us what our increment is limited by, how many new subarrays that we have. That'll tell us the limit of that. And so this is what I mean in terms of the formula. We know that the original comparison was zeros squared is less than or equal to ones. Like, that's valid. So let's take the difference of these. Let's take ones and subtract it from zeros squared. Obviously, we have that over here. That's going to give us 1, which is 4, minus 2 squared. So it's going to give us 0. That tells us that ending over here, we have exactly 0 extra ones. That doesn't mean that the entire array ending there is invalid though, because we know that the entire thing has 0 extra ones, but that's still perfectly fine because the inequality says that they could be like equal. Being equal is fine. So we would take this difference and then do a +1 to account for the fact that the entire array is considered valid. And then we would take that and add it to the result. This value could never be negative because we're going to have like an if statement guarding against that. We'll do that, like check that 0 squared is less than or equal to ones. So that's like the case. But imagine, just to make it a bit more interesting, that instead of there just being a single one over here, there were actually 2 ones. So then the math would be a little bit different. So I think for ones here, we would have 5. So there would be a 5 and there'd be an extra 1 at pointer 6. And then this would be at pointer 7. So there would be 2 cases. Remember, the first one would be that maybe every single one of these would contribute. So possibly we'd get a +3. But we also know that it's actually limited. Like, that's the upper bound, but it could be limited by the number of ones minus zeros squared, the surplus of 1. So we know in this case that's going to be 5 minus 4. That gives us a surplus of 1. So we have 1 extra 1. We have 1 extra 1 to lose. So that means that even if I got rid of this last one, this would still be valid. And remember, like I said, those ones are going to be contiguous. That's why it works. If the ones weren't contiguous, it wouldn't work. But in this section, they're going to be contiguous. That's why we hop from 0 to 0. So we get rid of 1, and we still have a valid subarray to lose. So that's why, or we still have the valid subarray. So we have 1 to lose. But anyways, so that's why we do the difference between that, which is 1, plus the 1. So we have 2 and 3. So among these two, we're going to take the minimum of them, whichever one is smaller, and that's what we're going to add to the result. This is the best case, and this is the worst case. Now you might be thinking, well, if this is the worst case, why don't I just add that? And actually, the reason for that is that this could actually theoretically be bigger than this one. I was just trying to oversimplify it. It could theoretically be bigger than this one. And the reason for that is, what if everything here that we saw up until this point was just a 1? Well, just because we have a surplus doesn't mean we can go further back than this orange line that we had originally. We don't want to double count some arrays that we had before already. So that's why we set it to the minimum of these two. So 3 is, if we could add everything in here, that's like the upper bound, and this is like the lower bound, even though this value could end up being bigger than this one. That's why we take the minimum of these two. If that was confusing, I'm really sorry. Imagine how confusing it is trying to explain it, let alone even understand it. It took me a while to understand it myself. But if you didn't understand some of this part, highly, highly recommend dry run through the code on pen and paper. I promise you that's the best way to understand this stuff. That's what I do. That's what all the smart people do. For this real example, I believe we would get, this was a 4, so we would have gotten that 0, and then we would have just gotten the +1. So then we would have counted 5 subarrays starting from here. Just to quickly go through the rest of this. Actually, I don't think I even have time for that, but this entire part was the hardest part. If you start from here, you'll initially start with 0, and the case won't even execute where ones is greater than or equal to 0 squared, so we don't have to worry about that. Anyways, I'll show you the final code. and then you can dry run it yourself, even if you don't fully understand it just yet. But I think it's pretty clear that the time complexity is going to be n times square root of n, because this is the number of times we're actually iterating for each starting position. So let's code it up. So I'm just going to start out with how I initialize the next zero array. I think it's not super complicated. I did kind of cover it in the drawing explanation, but we won't start at the last element. We'll actually start at one element before that, and we'll check if the next element to the right of it is 0. That's why we don't start at the last element. We don't want to get an index out of bounds. So we'll check if the next one is 0. Then we'll say if it is, well, the next 0 is just the one next to it. If it's not, we'll just set the value from the next 0 array, which could be n if there isn't a 0 to the right of it just yet. And we'll take that and then put it there. Okay, now for the actual code, I'm going to initialize my result, and then I'm going to kind of do a sliding window. It's not quite a sliding window, but it's kind of a brute force with some optimization. We're going to have a left pointer, which is going to iterate over the entire thing. I'm going to return the result out there. Here, I want to initialize the number of zeros because that's the one that we're going to be incrementing. Ones can be computed after that. So I'm going to set this to 1 if the value that we see is a 0. Otherwise, it'll be a 0. And I'll then initialize my right pointer, which is initially going to be left. And then I'm going to start iterating. While I could do this while right is less than n, we know that in some cases the right pointer actually is going to be equal to n, and we do want to count that window. We do want to count the window that ends at the end of the array. So I'm actually not going to put this here. I'm going to add something similar inside of the loop. So just to have a placeholder, I'll put a break statement right there. So the main condition, terminating condition, at least for this, is if the number of zeros squared is ever bigger than n. So that means if it's less than or equal to n, which is the size of the input string, then we're going to keep going. And so I want to find now my next 0. And then from that, I want to calculate the number of ones that we have. We know that the number of ones is pretty easy to calculate if we have that next 0 position. So it's going to be just this, next 0 from index r. But like I said, there is an edge case. There is the edge case that what if r is actually exactly equal to n? We still do want to consider that case. So we'll put a little ternary operator. We'll do this if that's less than n. Otherwise, we'll set it exactly equal to n. Okay, now that we have this, we know that this is our right boundary, but we're not including the value at this position. So that's why when we calculate the size of the window, we're doing this, next z minus left, but we're not adding the +1 because this is not inclusive. Here's a little comment to make that clear. But so the number of ones then is going to be the size of the window subtracted by the number of zeros. Okay, now we have that. Now is the case where we add to the result. As long as the number of ones is greater than or equal to zeros squared, we will add to the result. And remember how much we're adding. We are adding the minimum of these two values, the number of elements that we just added. So that's going to be from the right pointer to the next pointer. That's going to be the difference between them. Next 0 minus right. And the other is going to be, well, what's the surplus of ones that we had to begin with? Because we definitely can't add any more than that, even knowing that the ones are continuous. So the surplus is going to be this, ones minus zeros squared. And then to include the original array, we add a +1. Because if the surplus is like 3, well, that means we can have those 3. We can have just 2 of them. We can have just 1 of them. And we can also just have 0 of them. So that's 4. So that's why we take the surplus +1. Okay, now that we have that, next thing that we'd want to do is this. Right is going to be equal now to the next pointer position. We could have also just assigned it to this, but since we already have a variable for that, I might as well use it. And we also are always going to increment the number of zeros by 1 because we're hopping by that much. So notice how we're incrementing this by 1 each time, and then we're terminating by this. So that proves that this loop is never going to run more than the square root of n times. Because if it did, this condition would no longer hold. Okay, you can probably guess what's going to go here. Basically, if r is ever equal to n. And actually, now that I think about it, that makes me wonder if this was actually ever needed to begin with. So actually, before I investigate that, let's just make sure that this code works, and then maybe we can actually simplify it a bit because, okay, so that does work. So I think I explained it mostly correct in the drawing explanation, but I confused myself here. I think the difference is that while next 0, the next pointer, yes, it can go out of bounds. It can potentially equal n, and if that ever happened, then we would assign r to that, and then we would break out of that early, because r is actually part of the window, but next 0 is not. So r can never be equal to n. If it is, then we would exit, but next 0 can be equal to n. So let's just make sure that's the case by running this. Okay, so yeah, it does work. So yeah, but anyways, you can see how insanely complicated this problem is. Like there's many variations of solutions to this one. I tried to come up with one that was pretty straightforward. I think there's one, the Leetcode editorial uses like a different convention using previous 0, which I think is a bit more confusing. I thought my convention was probably the most straightforward, but anyways, I'm probably going to go and do something else with my life. But this was a fun one. Hope you guys enjoyed. Check out Leetcode.io for a lot more.